Wei from Zhongzheng Christian University, and it's my honor to give my speech in front of professionals and professor doctors as a master students. Okay, my title is Model Analysis and Static Structure Analysis for 3-axis cartoon robot used in injection molding machine. I'll start with the background, and I'll begin with the model testing, then introduce the model analysis, then we'll discuss the results between, then make a conclusion. As we know, our life is full of plastic products such as our phone cases or screwdrivers or gears, maybe vehicles, gear parts that was all made from plastic. And there's a method. It's called injection molded plastic. That is a kind of method that we produce plastic products. And this kind of market is valued at $303.8 billion USD in 2020, and it will be predicted to surpass around $433.53 billion by 2032. So, which is the market of the plastic injection will be growth year by year. My research is collaborated with Hymo Corporation, and this plastic injection molding will be set. This robot will be set on the injection machine, and this is how the injection machine and the robot look like. At the right of the slides, you can see so the robots will be attached on the injection machine, as the picture shows. This is the STP-900. It is a cardigan robot that with high speed and high precision, and it is light and rigid. This kind of a robot will take out or insert any parts into the mold to create different materials products. To begin with, the robot, it has a base, and there's a barrel on the top, and then there's a wing and the main arm of the robot present in the picture. This is the process cycle of how the robot works in plastic injection molding. So first, the robots will pick up the gears or inserting parts, and then it will insert into the mold. And then the plastic injection machine will inject the plastic that is melted into the mold, and the robot will take the products out. So the problem is when the robot is inserting anything into the mold, it has a vibration that caused with unknown reasons. And my research is to figure it out why the vibration occurs and how we to suppress the vibration at the second process of this cycle. Okay, so. And it includes two methods. The first is the model testing as the real experience of model analysis, and there's a second simulating for the virtual simulation of the model. We use the finite element model to simulate the whole process of the robot, and using the experiment parameters to calibrate and validate our simulation. I'll start with the model testing. This is the geometry model of the robot STP-900. First, we will add some knots on the robot to give us the feedback and collecting data, and we'll excite the robot to create vibration that will cause the whole structure vibrates. Then we will collect all the data into the dynamic signal analyzer and transform it in the frequency to the frequency domain, and to calculate and extract the model the transfer function of the model. This is the knots to figure it out where the vibration occurs, and to examine the whole structure if it's rigid or sturdy enough. The knots will increase the density in the connection parts of those robots, such as the base and the barrel, and including the main arm. There will be more knots on it. On the left side of this slide, I showed how we attach the accelerometer on the robots. It will attach with magnet or a wax, depends on the location of, depends on the materials that we use as the parts. And I use the impact hammer to create excitation to vibrate the whole structure of the robot. The model test will collect the frequency response from the accelerometer and collect it into the dynamic signal analyzer and use the fast-forward transform to transform the time domain to frequency domain, and then we will import those data into Cloud PC as a software in computer. On the left side of these slides, I show the frequency response function and how I select those poles to extract the modes. The poles represent the stable and how the real modes appears in the frequency domain. So this is the results of model testing. It will give us the damping ratio, the mode shapes, and the natural frequency of the STV900. And we only set up the frequency window from 0 to 200, and we found the first 3 modes of the STV900. And the GIF shows how the robots vibrates. And now let's move on to the model analysis. The whole workflow will start with importing the model, and we'll remove some details from the models, and we'll set up some boundary conditions to simulate the real scenario of the robot, and we'll add in the material properties, then we'll do the mesh. So this robot is kind of simple. It's just attached on the machine, so the boundary condition will be fix the base part of this robot and make sure all the parts from the robot will be attached with rigid or maybe flexible. And then we'll set up and import the materials of the robot. This robot content including the aluminum and the steel. The material properties will include the temperature, will include the Poisson factors, the density, and the Young's module. Then we'll do the mesh. The mesh is quite important for the finite element model, and we use the free tetrahedra to create plenty elements for the robots. And we will increase the density as well, specifically for focusing on the small parts of the robot. And to get a better simulation results, we will adjust and simplify the robots as they to increase the quality of elements. The quality of elements will start from 0 to 1. If the quality score is higher, close to 1, it means the quality is better. So when I simplify those small details of the robots, the mesh quality will increase from 0.47 to 0.6. And the quality of mesh might increase the simulation time and will cause more memories of the computer that it needs. This is the results of the simulation. From the left side of the column, it's the real number of the experiments, and the right side is the simulation. We can see it is quite different compared to the real and the virtual simulated, since the virtual model of the robot, we skip many details of it, so the natural frequency will be higher since it lose some mass and lose some rigidity, so the real number of the frequency will be lower than expected. And the damping ratio will represent how the energy is passed in the model structures, and the simulation of the damping ratio will be much lower since there are many wires, bolts, and holes will cancel in the virtual model. So this is it moves very fast. This is the comparison of the real model and the simulated model, that how they vibrate in the finite element model and the animation. To improve the finite element simulation, we will use the boundary conditions we will try to figure it out where it is not correct, and we will adjust the model to improve the complexity of the model that represents more like and close to the real structure of the robot by adding some motors or blocks to represent the control box or supportings. It's a more like easy way to adjust the model. But the real method is to set up the loose mass matrix. As a conclusion, this study, we implement the model testing and simulate the virtual model that we present in finite element, and we show those parameters that might help us to create and design the better structure of the robot. Thank you.
This presentation is open to discussion.
Okay. Yeah. So you is just modeling is whole is one body, right? So it's many parties combined to the whole robot, right? So it's the linear guide, part linear guide is combined with the bolting or something, the whole content. Understand? So you just the simulation is just whole is one body. So you can the contact any part is a contact, right? It's with simulation is a contact condition. So this is let's think about that. So have a spring damping spring the condition or something.
Connection.
Part is a
Condition.
Right?
Yeah.
So you have to separately, whole part is separately the simulation, and then the part is a contact. Okay. So this is possible.
Yeah.
Try it. This is more correct result.
I'll try that. Thank you for advising.
Is that one more question for me? Actually, the reason why you guys analyze why this machine vibrates when pick up the injected molded object. However, eventually you guys have a goal to reduce vibration, right? So this is the stage to what causes this vibration, right? And then of course you guys have a little difference with between real model and simulated model, but eventually you guys have to reduce this vibration. Do you have any idea to?
Well, so this research is the first stage of my whole research. We will examine the structure of the robots, and moving to the next stage, we will design a control system to avoid those natural frequency to decrease the chanceability of resonance that occurs during the operating.
Do you guys have any more questions? Okay, thanks to